For most functions, using trapezoids to approximate areas is more accurate than using rectangles. The area formula for a single trapezoid is 1/2 height times the sum of the bases. Since trapezoids used in the approximations of areas are usually positioned vertically, we will write the formula as 1/2 times the width times the sum of the heights. To approximate the value of a definite integral using trapezoids, use the same strategy used for the Riemann sums, but add the area of trapezoids instead of rectangles.
Approximate the integral from 0 to 10 of f of x with respect to x by adding the areas of the 5 trapezoids shown in the graph at right.
The width of our first trapezoid is 2. Height 1 is 0. Height 2 is f of 2, which is 4. For trapezoid number 2, the width is 3, the first height is 4, and the second height is 3. The width of trapezoid number 3 is 1, the heights are 3 and 2. The width of trapezoid 4 is 2, its height number 1 is 2, and height number 2 is also 2. The width of our last trapezoid is also 2, height number 1 is 2, height number 2 is 5. And those areas are our approximate area under the curve using these 5 trapezoids is 28. Notice that the area formula for a trapezoid also works for a triangle where your height 1 or height 2 could be 0, or it could work for a rectangle where height 1 is equal to height 2.
Use 4 trapezoids of equal width to find an approximation for the area under the curve y equals x squared, bounded below by the x-axis, on the left by x equals 0, and on the right by x equals 2. Sketch the curve and draw the trapezoids first.
Begin by graphing. Our left boundary is x equals 0. Our right boundary is x equals 2. 4 trapezoids of equal width would give me a width of 1/2 for each trapezoid. Fill in the trapezoids. If you didn't want to graph or you couldn't see visually what that width should be, remember that width is equal to b minus a over n, number of trapezoids in this case. We're really approximating the area of this integral by taking the area of 4 different trapezoids. This time we will use our function y equals x squared in order to find some of our heights. To begin, each of our trapezoids has a width of 1/2, and each trapezoid formula has 1/2 times the width. Okay, so I set up the areas for each of these trapezoids, and now we just have to determine their heights. Our height for the first one was 0, and its second height was the y value when x is 1/2, which is 1/4. Our next trapezoid has a first height of 1/4, and its second height is 1 and 9/4. Finally, 9/4 and 4. Notice how each of these areas has a 1/2, since the area of a trapezoid always has 1/2 times, and then there was also the 1/2, which was the standardized width of each trapezoid. So I'm going to actually factor those out of my sum. Notice how each inner height will be used twice, one for the trapezoid to its left and one for the trapezoid to its right. It's only the first and last values that are used only once. 1/4 and 1/4, 1 and 1, 9/4 and 9/4. So we can actually create a formula for the trapezoidal rule. 2 times each of the inner heights. This is equal to 11/4. And you guessed it, AP needs to see the entire sum as well as the result. When using trapezoids for approximations, if the subdivisions produce equal widths, then we can use this formula. 1/2 times the width times this quantity. The addition of all the heights, except the inner heights, will be doubled.
Use the trapezoidal rule with 4 equal subdivisions to approximate the area shown.
The width of each of our trapezoids is 10. So my area is equal to 1/2 times the width. And now we will add up each of our heights, but double the inner heights. Notice we'll be getting the y values from this table. Our final answer should have the sum, and it's equal to 100.
Note the similarities and differences between the trapezoidal rule and the formula for finding Riemann sums. Each adds areas by multiplying a common width by a sum of heights. When using trapezoids, you have a half the width, but twice the heights.
And that's the trapezoidal rule.